Compute this matrix to the nth power, 1110, for small values of n up to about 5 or 6. Conjecture explicit formulas for the entries in this matrix and prove your conjecture using mathematical induction. Let's start by raising this matrix to the 1th power. This doesn't really do anything, and so we get the same matrix that we started with. Next, we can raise this matrix to the 2nd power, which just means that we need to multiply this matrix by itself. And we get this matrix 2, 1, 1, 1. Next, we'll cube this matrix, which is the same thing as the previous result times another factor of the original matrix. And so next we get 3, 2, 2, 1. And the way we're determining this is we're multiplying the rows of the first matrix times the columns of the second matrix to get the corresponding entry in that corresponding row and column in the solution. Next, we'll raise this matrix to the 4th power, which is the same thing as the previous result times another factor of the original matrix. And I'm noticing that this result contains numbers in the Fibonacci sequence, 2, 3, and 5. So far, we haven't seen any like 4s. Next, we'll raise this matrix to the 5th power, which is the previous matrix times 1, 1, 1, 0, which gives 8, 5, 5, 3. That 8 there is definitely confirmation bias. That 8 there is definitely confirming that I think these numbers in these entries of this matrix are all Fibonacci numbers. Now it tells us to go to 5 or 6. Let's go to 6 just to make sure. Now my conjecture is that this is going to be, instead of 8, 5, 5, 3, it'll be 13, 8, 8, 5. But let's see if that's actually true. And sure enough, it is. So now we can start to make some conjectures for explicit formulas. So we can say that raising this matrix to the nth power is going to give us a 2 by 2 matrix where all of the entries are Fibonacci numbers. Now this is only going to work for n greater than or equal to 2. Since when n equals 1, we actually have this entry of a 0 here, which is not a Fibonacci number according to the definition of this textbook. But that's fine because this formula is only useful if we're raising the original matrix to an exponent greater than or equal to 2 anyways. What we have to do is we have to figure out what the relationship is between the exponent and the corresponding entries of this matrix here. Now keep in mind that f sub 0 equals 1, f sub 1 equals 1, and f sub 2 equals 2. So I'm noticing that since the top left entry here is 2 and the exponent is 2, then the top left entry is just going to be f sub n, whatever this exponent is. So I'll put an n here. But I'm also noticing that the top right entry and the bottom left entry are always the same. And they seem to be the Fibonacci number prior to the one on the top left. So the top right Fibonacci number should be n minus 1. And the bottom left should also be n minus 1. And then the bottom right number should be the Fibonacci number before f sub n minus 1, which is f sub n minus 2. And this is the explicit formula that we want to conjecture. Now we want to verify the correctness of this formula using mathematical induction. We'll say that this is our P of n, and we'll start with our base case, which is n equals 2. So P of 2 is the statement that if we square this matrix, we get the matrix f sub 2, f sub 1, f sub 1, f sub 0. I put a question mark here because we don't want any circular reasoning. We're going to evaluate both sides of this equation separately. Now, we actually already have the work for the left-hand side. We calculated the left-hand side earlier and got 2, 1, 1, 1. So that's the left-hand side. The right-hand side is this matrix with a bunch of Fibonacci numbers, f sub 2, f sub 1, f sub 1, and f sub 0. F sub 0 and f sub 1 are both 1. And f sub 2 is 2. So this is 2, 1, 1, 1. And if you notice, we get the same result on the left-hand side and the right-hand side. And so therefore, P of 2 is true. Now let's move on to the inductive step. So we start mathematical induction pretty much the same every time. Let k be an arbitrary fixed integer with k greater than or equal to 2, which is the base case, and assume that P of k is true. Let's detail what P of k actually is. So this is our inductive hypothesis, which is P of k. We want to show that if we raise this matrix to the k plus 1th power, we get this other matrix with these Fibonacci numbers. Now to prove this, we're going to start with the left-hand side here. Now we want to use our inductive hypothesis. Our inductive hypothesis tells us what happens when we raise this matrix to the kth power, but that's not quite what we have here. And so what I'm going to do first is I'm going to rewrite this as the multiplication of two matrices. One where the exponent is k, and then this other matrix which is just one more factor of the original matrix. Now we can apply our inductive hypothesis. The inductive hypothesis tells us what this matrix is. And so we're going to substitute this with this matrix that we get from the inductive hypothesis. And so we can substitute this matrix using our inductive hypothesis. Since we're using the inductive hypothesis, we need to tell the reader that we're using the inductive hypothesis. So we'll put here by the inductive hypothesis. Now what we wanted to show is that this matrix is equal to this matrix with the Fibonacci numbers. We're almost there. We just have to multiply these two matrices that we have. If we multiply these matrices together, we get a matrix with these Fibonacci numbers. Now, this isn't quite what we wanted, but if you notice, the only difference is this top left entry. So we have to do something with this top left entry to get what we wanted to show. The trick, though, is knowing what the Fibonacci sequence is. By the definition of the Fibonacci sequence, if you add any two consecutive Fibonacci numbers, like for example these two consecutive Fibonacci numbers, then you get the next Fibonacci number. So by the recursive definition of the Fibonacci sequence, this is f sub k plus 1. And that proves that p of k plus 1 is true, which means that by mathematical induction, this p of n is true for all n greater than or equal to 2. Thanks everyone, and I'll see you in the next video.